All right. Hello, everyone, and welcome to the ME seminar series. It is my pleasure to invite today and to introduce today Professor Michael Haberman from the University of Texas, Austin. Professor Haberman got his PhD in 2007 from Georgia Institute of Technology and spent some years in France as well, where he got a diploma, the doctorate in mechanical engineering from the Université de Lorraine in Metz, France. Before joining the University of Texas, he was a research scientist at Applied Research Laboratories at UT Austin. He's an associate editor of the Journal of the Acoustical Society of America. He is the technical committee chair of engineering acoustics for at the Acoustical Society of America. Actually, he was elected fellow of the Acoustical Society of America in 2020. He received a Young Investigator Program Award from ONR in 2018, and last year he got the Young Faculty Award from DARPA. He is a leader in metamaterials. He activated in this field for a long time. His interests are on a wide range of metamaterial topics that go from the development of new transduction materials to the manipulation of physical waves and cloaking. So with this, I would like to, invite Mike to give a seminar. You have your floor.
Okay, all right, you can hear me okay? Very good. Okay, so for those of you that are online, I think you just get my voice over some slides. So I apologize for that. If I'm moving my arms, you'll just have to ask others what my antics were, I suppose. So, okay, so today, thanks Bogdan for bringing me up here into the Great White North. It's great. I really appreciate everybody entertaining me for the day. So the topic of my seminar that I chose is on non-reciprocal acoustics. I'm going to talk about it. This is a topic we've worked on through an NSF program and a few other programs for a few years. So I want to talk about some of the concepts and then a little bit of a practical application of it to sound diffusion and some ideas for maybe interesting implementation. Okay, so I already got a little bit of a background, so I won't bore you with the details of where I came from. Kind of got a long history, a long pathway to where we are right now. Starting at the University of Idaho in 2000, and then also spending some time at GN Resound in Chicago, working on the design of hearing aids. And actually we were building in 2001 to 2003 some of the first additively manufactured hearing aid shells and systems, which was actually a really fun experience. Okay, so today what I want to talk with you about is a couple of things. I'm going to talk specifically about the idea of acoustic reciprocity. Many of you probably know what that is, at least big picture, and maybe you've applied.
We lost the picture.
I think you're good. Okay, can everybody hear me online? Sorry, I think we might have lost you for a second.
Yes, we can hear you again.
Okay, very good. All right, so let's go back to where we were. All right, so I'm going to take a little bit of a jump then. I'm going to talk from kind of big picture concepts associated with the ideas of sound diffusion and audio systems. That does have some application to stealth as well. And then acoustic metasurfaces and these concepts of spatiotemporal modulation of surfaces to control the sound field. Okay, to start with then, I'm going to talk about the idea of reciprocity. And I like this one kind of halfway as a joke, but you know, the oldest version of reciprocity I can think of is the eye for an eye, right? So, but in acoustics, what we primarily talk about and what we mean when we talk about reciprocity is really was outlined quite some time ago, initially with some work by Helmholtz and a few others earlier as well. Rayleigh ultimately kind of provided the first mathematical proof and details in his theory of sound. And specifically what he said is if you have some inhomogeneous medium, even in the presence of losses and variation in properties, if you have a source of sound at A, you'll get a resulting velocity potential at B. And then if you interchange the source to be placed at B, then you will get the same resulting velocity potential at A. And then in his own words, this is basically what he had to say. So this was a really interesting problem that a lot of people sort of wrestled with from a mechanics standpoint. Folks like Lagrange and Maxwell looked at this. There's a lot of work with the Onsager and Casimir principle and microscopic reversibility that describes this in terms of material properties. And on the static standpoint, Betty looked at this in terms of force and velocity fields for force and displacement fields for elastic medium. But it's this very fundamental principle that is actually in practice very difficult to violate, at least on purpose. And so because of that, it tends to be used actually quite a bit in science and engineering. We use it to calibrate microphones, to do absolute calibrations via reciprocity measurements. Not many people tend to do those because they are time consuming and you've got to be really careful to do them correctly. One interesting utility of the idea of reciprocity is actually these concepts of time reversal mirrors, where you want to maybe focus an acoustic sound through an aberrating field, which may be lossy or which may be just inhomogeneous in general. So one way to do that is you take a source of sound, you surround it with a surface, a measurement surface, you play a signal, you measure that signal at all points, you time reverse that, and then you send it back through, and it'll focus through any arbitrary medium. So Matthias Fink at Paris has been working on this for years, has done a lot of really cool stuff with it. But even ideas like just pulled this from the news, just a few weeks ago, the idea of this eruption, we know because we can run things backwards in time. Not only can you measure an event like this eruption, in Tonga eruption, you can not only get an estimate of where it occurred if you didn't know, you can also get an idea of the magnitude of that eruption based on the idea of reciprocity and time reversal symmetry. And so the motivation for some of our work going back quite some time is this idea is, can we engineer metamaterials or media in general that will allow us to...
My quick question on time reversibility. Is it always time reversible or there are some criteria that has to be met?
For time reversal for the time reversal mirrors? You can dig down a pretty deep rabbit hole in there, but generally you can assume just time reversibility, that you literally record your signal and you flip it in time and you play it back. Yeah. And so the challenge we kind of set for ourselves, I should say NSF set for us, was to say, what is it that you can do to actually purposefully make a medium such that when a wave propagates in one direction, you don't get the same thing as it propagates in another direction, and the reverse. And there's a lot of interesting concepts here in regards to vibration or acoustic isolation. STAR, this is something called simultaneous transmit and receive, where you can transmit and receive on the same antenna, maybe at different frequencies or at the same frequency in opposite different directions. Immunity from backscattering, maybe you want to absorb something, but also be able to emit from the same surface. And you know, some of these ideas initially came out of work that came out of a collaboration that Andre and Alou and I had, where we showed that you could essentially take what is a degenerate mode in a cavity and introduce flow inside that cavity in order to break the degeneracy of the mode and to split it into an asymmetric mode in order to steer a null and transmit a wave from one port to another, but not back. So if it's incident from here, it goes out here, but not this way. And then if it's incident from here, it goes out here and not this way, and all the way around. And that's what's known as an acoustic circulator. Okay, so that's kind of this overall arching goal. And what I'd like to provide is a little bit of context. And specifically, there can be some misconceptions with respect to what is reciprocal versus asymmetric transport of acoustic energy. And so let's look at a really simple problem. Let's look at a 1D problem where I've got a time harmonic wave incident from one side on a slab of material, normally incident, propagating in the positive X direction. When I do that, I'm going to get one wave, a wave transmitted from that incident wave and a wave reflected. I can take the exact same material itself, and I can have a wave incident from the right-hand side then, right? And I can then classify some transmitted wave from that incidence from the right-hand side and a reflected wave from incidence from the right-hand side. And I can describe this using a nice scattering matrix representation, which is a two-port representation, where I have in general incidence from the left. These are incoming waves related to outgoing waves for this port, in this case, two ports, in or out in one dimension. And we have these scattering coefficients, S, 1, 1, 2, 2, and 1, 2, 2, 1, which represent the reflection coefficient from the left-hand side, the reflection coefficient from the right-hand side, and the transmission coefficient from the left to the right and the right to the left, okay? And these just calculate what those fields would be. And I really should have almost made this a little bit bigger, because one of the things that's important to remember is that for a medium to be reciprocal, okay, we have a medium that's reciprocal, non-reciprocal, symmetric, or asymmetric, meaning in terms of its acoustic transport. And what I mean by that is if it's reciprocal and symmetric, then the reflection coefficients from both sides are the same, and the transmission coefficient from left to right and right to left are the same. If it's reciprocal and asymmetric, then I still have symmetric transmission. If I interchange source and receiver, I get the exact same signal. But I can actually design a system, actually not terribly difficult to do, where the reflection coefficient is different. And a very extreme example of this is an anechoic chamber, okay? If I'm inside the anechoic chamber and I clap, the waves, I have a wall, I clap, I get no echo back. I get a perfect absorber, perfect, right? If I go outside that wall and I clap, I get a really strong reflection. In both cases, I get almost no transmission. In one case, I get perfect reflection. In the other place, I get perfect absorption. So that's an asymmetric absorber, kind of in the extreme, okay? So non-reciprocity, on the other hand, is the case where you have maybe a symmetric case where reflection coefficients are identical, but transmission coefficients are not. And then the most general case is where you have neither reflection nor transmission is the same for incidence on the opposite sides. Okay, so that's just a nice single two-port system, input, output, left, right. In general, though, we can look at this in a slightly different way. And this is very relevant to what I'm going to talk about in terms of receivers, diffusers. Imagine you have two waveguides. One waveguide, even though forget how it's drawn, this is infinite to the left, connected to another waveguide that's infinite to the right. And in the middle, I've got a mode converter. And what I mean by that is that imagine I've got an incident plane wave from the left. I have something inside here that converts that to, so it's sort of a symmetric mode that's incident. And then I have a mode converter that then converts it to an asymmetric mode in that waveguide. So in this case, I have reflected mode 1, reflected mode 2, transmitted mode, reflected and transmitted mode 1, reflected and transmitted mode 2. Okay, so I have actually a bit more. I have a three mode system, a 3-port system. So in this particular case, if this is a reciprocal system, I will have an incident wave that will convert from mode 1 to primarily mode 2, right? And then if I flip that and I have an incident wave from the right, I will get conversion from mode 1 primarily to mode 2, as you would expect. Okay, and the reason that one may think that this would be, that this may be asymmetric, or sorry, non-reciprocal, is if you imagine that if I went to this particular case right here, if I put a mirror on the right-hand side, right, then what I should recover is I should recover a plane wave on the outset. So now one thing to remember is sometimes early on when people are talking about reciprocity, they often were confusing symmetry and reciprocity. Because as I'll show in the diffuser, you can convert, these conversions to different modes are not always in the same direction. So you can trick yourself into thinking that I convert fully to mode 2, which may go off in a different direction. Imagine conversion to shear mode from a longitudinal mode at an interface of 2 solids, for example. And if I try to return mode 1, right? If I try to return mode 1, I'll get back mode 2, right? So incident mode 1, transmitted mode 2, incident mode 2, get back mode 1, or sorry, incident mode 1, I get mode 2 as you would expect, okay? So this is just plain and simple saying that this is a linear and passive system that will require that the Sij has to equal Sji. Okay, so the transmission coefficients have to be the same. Okay, it's reciprocal, but it's asymmetric because now if I reverse this in time, I perform a time symmetry inversion, then I recover the same wave in or out as I put in. Okay, so in order to get the wave out that I put in as I reverse in time, that's the proof that the system is reciprocal, although you are converting in modes. Okay. Okay. So then what is non-reciprocity? The thing to remember about this is it's not easy to overcome, even though it may seem like it may be. And the reason is that systems that are linear, passive, and display time reversal symmetry are reciprocal. It is actually rather complicated because nonlinear systems, just because a system is nonlinear does not mean that it will be non-reciprocal. There are actually certain conditions that are required, such as asymmetry. We wrote a pretty lengthy review article on this in 2020, where you can you can bore yourself to death with it. But there are a lot of fine details, and as a matter of fact, the difficulty in all this is that in order to create a medium or a structure that is non-reciprocal, you have to violate one or more of these behaviors. So how do we do it? There's a couple ways. Most primary ones are sort of active or momentum bias materials or systems like the circulator that I showed you before, or transverse or propagation through a fluid medium with flow, for example. There's also this Bogdan's paper from 2014 where he showed an active system that could do the same thing. Nonlinearity is a common one where you, for example, you have a wave incident at F0. You use nonlinearity to convert up to 2 times F0, 3 times F0, and use frequency selective mirrors as filters, such that waves only propagate from one direction to another. And actually that's more energy propagating one direction or another. And the other one is to modulate properties, specifically in space and time, as I have shown here, where basically as an example, the Young's modulus and the density becomes not only periodic in space, which we can imagine with layered materials, but also that those properties actually tend to translate in time, which is clearly a difficult thing to achieve in practice. But that's where I'm going to look. And the reason I'm going to look there is that we've actually done a fair amount of work in looking at small on large acoustic or elastic wave propagation, where, for example, we impose a relatively large finite deformation on an elastic network, where locally the effective moduli, the shear moduli, the plane wave moduli change with pre-compression. And then we propagate acoustic waves on top of that. And so as I change the modulation, the finite modulation at rates that are much slower than the acoustic wave propagating rate, then I can generate elastic wave non-reciprocity. We also know that we in potential or possibly could use electroacoustic or electromechanical coupling in order to modulate properties and or surfaces. Okay. So all that to say, this is hopefully give you a little bit of idea of reciprocity. It's a hard thing to nail down in a brief amount of time, but hopefully they give you a little bit of an idea. And now I want to switch gears a little bit and talk about diffusers, okay? And the reason I say this is that we've shown, or sorry, let me say it this way. These modulated properties, we've shown a pretty distinct way to be able to do it, the mathematical let's say toolbox to be able to evaluate whether a material in and of itself would generate non-reciprocal wave propagation. But the ability to implement that in practice is really difficult. As a matter of fact, it's a significant scientific challenge and a technical challenge. I think there's a lot of things you could do with it, but we need to do more research to figure out how to make it useful in the bulk, right? Now, bulk material. By engineering surfaces, that's potentially an easier path to show some of the results of the other research that we've done, where we control the acoustic field that is reflected from the surface. Okay, so let's take a step back and let's talk about an acoustic diffuser. So acoustic diffusers are basically sound, we call them sound diffusing surfaces, right? These are surfaces that are made to reduce the strength of specular reflections, like from the back wall, side walls or something like that, that cause audible echoes that are distracting or generally lead to poor intelligibility in the space. And also room modes. So if you have a small room like a recording studio and you want good sound quality throughout the room, you don't want any given room, any given mode to exist because you can have high concentrations of sound power in one location of the room and not another. So you can be playing your bass guitar and have your microphone in another spot and actually not even be able to hear how loud it is right over there, okay? So that's kind of the original design, concept of these things, and you see them throughout. You'll see them in some restaurants and you'll see them in recording areas and things. So classical sound diffusers are actually, usually you've seen these. They're irregular surfaces. They're 1970s technology, if you want, right? And the idea here is, a 1D diffuser, you can just imagine it's basically just a plane wave comes in and you've got these wells where a wave comes in and it sees a little cavity, which is like a little acoustic compliance locally that changes the phase of the reflected field locally. Okay, and you can choose then the sequence of that randomness in some mathematical sort of pseudo-random representation in order to increase the diffusivity of sound. Okay, and the idea being that for any wave coming in any direction, energy gets scattered off equally or at least largely in many directions, all by the same amount. And you can generalize this to 2D without too much difficulty. And you can see how this looks. This is actually Schlieren images of a acoustic spherical point source interacting with a pretty large diffusing surface. And you can see how you have this nice coherent wavefront incident. And then after it goes through the process of interacting with the diffuser, you get pretty drastic elongation of that wavefront in time and energy propagated out in multiple directions. It's not a nice point reflected spherical wave outgoing. Okay, so these are generally known as Schroeder diffusers from Schroeder, who originally did a lot of interesting work in architectural acoustics. And as I said, the idea here is plain and simple to design well depths in a classic sense in order to get the scattered field that you would like. And the idea, the mathematical description of this is pretty simple. It's a grading equation where basically you can decompose for an incident sound wave at angle theta I. It interacts with the surface here that has a spatially dependent impedance, input acoustic impedance. And so you have your projections of your wave number, Kx and Kz, according to the incident wave direction. And then, so there's your acoustic wave, your incident acoustic wave. And then your scattered wave, you're just going to assume is a summation of Bragg orders, of diffracted orders, that are based on projections along X and along Z and of unknown amplitude A sub n. Those are the scattering amplitudes. Okay, and in this particular case, the wave number projected along n, because the diffuser in and of itself, although it may be quasi-random, it still repeats on some interval. And that interval on which it repeats is this lambda here, capital lambda. So the wave number for the acoustic field on that surface is given by the projection of the incident wave plus some multiple of wavelengths along that period. And then the scattering, the direction, or sorry, the wave number then projected of the scattered field is based on the difference of the wave number in the background field and the projection along X. And so therefore you can calculate the direction that you get these scattering orders off at. Okay, so you have the 0th order plus 1, or sorry, +1, -1, and -n, all the way out to however many modes, depending on the wavelengths and the like. Okay, and so the first thing that we did when we started looking at this problem was just looking at it from an acoustic metamaterial standpoint, was just plain and simple. Was like, can we actually make these thinner? Okay, so we did one, before getting on the reciprocity question, we said, well, first of all, these specific diffuser designs give you a different reflected phase based on this pretty simple equation, right? Where the depth of that well gives you the admittance, which basically tells you the phase of the reflected field. It gives the imaginary part of the admittance. Okay, and the maximum, basically the well depth dictates what the maximum amount of is based on the wavelength that you're trying to design this for. So if you try to design it for lower frequencies, you need deeper and deeper wells, classical problem, and any kind of wave-based equation or a wave-based problem. And so that can be problematic if you're talking a kilohertz or 500 hertz or something like this. So the very first thing we did is we looked at metasurfaces. And let me just explain really quickly why I'm going to show you this. Mostly it's to show you the experimental results we can get so that when we implement our modulated system, you can see the results that we have a system waiting to be able to make these measurements. So this metasurface is basically an acoustically thin interface where we can generate an arbitrary phase shift, okay, with an acoustically thin surface. So the acoustically thin, all that means is that it's much smaller than a wavelength at the frequency of interest. In order to do, or when we do that, we have a significant control of reflected, transmitted acoustic fields. And what that also means, not only the amplitudes, but also the direction. So these do not obey Snell's law, they obey something called generalized Snell's law, which is requires us to consider the gradient of the phase along this interface, okay? And so some people have done a little bit of work in this area. They've actually looked at what amount to little Helmholtz resonators, either little cavities like so, which are on the order of a 20th lambda. They work only really at very narrow frequency bands where you get the reflection coefficient or the resonance basically of the Helmholtz resonator, and they're not terribly effective outside of it. And then there's other ones where they're also a similar idea, but basically Helmholtz resonators that have a slightly different character because they're sort of Helmholtz resonators that are on their side. And so that allows you a little more tunability and a little more bandwidth. It's okay, it just sounded like it was kind of going quiet. What we were a little bit more interested in was seeing if we could do something that operated in a little more broadband sense. And there's these ideas of what are called coiled space structures. There's nothing terribly special about them. Basically, you add a little more tortuous path. So you basically you take your cavity that's this big and you crunch it down smaller. And the hardest part about that is just that you have to avoid thermoviscous losses. The more you try to compact space down, the more tortuous your path becomes. And so then the air basically gets confined in there and you get dissipation. A good diffuser ideally doesn't actually absorb much energy. You want to maybe keep the room live. Maybe you do want to absorb, but maybe you don't. And often you actually don't. So ideally, we've seen some in the literature on different kinds of reflections, some perfect absorbers, clearly not what we want. There's this group out of Bristol that did some interesting work on levitating objects in the Mamoli and Bruce Drinkwater. And they found these, which were quite low loss. And they were sort of a bit of a mix between a coiled space structure and almost a little modal structure inside. And they tend to be quite low loss and really give you a pretty wide range of control in phase. And so the idea here was just to take these 1D diffusers and to design the appropriate coiled space structure in order to replace each well by effectively doing numerical studies where we look at different building blocks. We do forward models by varying sort of the width and the depth of the arms within these coiled space structures. Okay, and then we find the same phase response as a given well depth in order to match the experimental result or the desired result that you would like to have. Okay, so I'm going to show you the measurement that we did. What we did is we basically went through and we looked at a 2D QRD. A QRD is something known as a quadratic residue diffuser. It's just a mathematical sequence. We picked that because it's one that's well known. Not really any specific reason other than that. And the classical one has a well depth designed of we have sort of a one period of it, about half lambda at 5 kilohertz. We built 4 of those so that the field's a little bit more uniform when we do the measurement. And then we designed a 2D coiled space metasurface diffuser, and we assembled those. One interesting point about these is because those little coiled space things are sort of quasi 1D, they have a directionality to them as opposed to just an open cell. This is just an interesting sidelight. You actually have to place those randomly oriented. You can't place them all in the same direction or it doesn't work as well, interestingly enough. Okay, and then what we did was we printed those out. We placed them, and I'll show you the configuration. We placed it on a pedestal. We excited it with an acoustic wave. You'll see on the next slide. And then we rotated it through different angles in plane in order to get a 3D surface plot of the scattered field. Okay, and so here what we've got is our measurement system, our nice little Arduino scanning system with a microphone. A little bit hard to see here, but we just took a microphone and we scanned it across a nice 180-degree arc. Our loudspeakers up above, we play a long duration chirp, use deconvolution methods in order to extract the impulse response. And we do measurements with and without the diffuser in order to then subtract scattering from all the clutter that exists out there. So we do have a bit of residual here, but you can see an impulse response that's sort of extended in time and in space. And this is effectively the impulse response at angle at about 180 degrees all the way to 0 degrees. Okay, so we then use that information for every single orientation of in-plane angle. Okay, so we get one plane of scattered field, we rotate it, we get another plane of the scattered field, and then we assemble those things, and we're able to make our nice little flower-like diffusion, diffused scattered field with the metasurface and the standard QRD shown here. These are effectively is a lot of data, so it's a little hard to tell comparatively speaking. We can compare these with something known as the diffusivity of the field and show that they're actually almost identical at 5 kilohertz, which is the design frequency. And the AMS is a little better at higher frequencies, interestingly enough. And that's probably because it's about 1/8 of the wavelength. as thick as opposed to a half wavelength. So it's about a fourth the thickness. Okay, great. So that was really more to kind of give you a little context for how you might engineer a surface to give you a nice diffusion of sound and how we might measure it and characterize it. It has nothing to do with reciprocity other than the system is fully reciprocal. So let's talk about what maybe might be interesting from the standpoint of spatiotemporally modulated sound diffusers. Okay, so when you look at that classical design, the real, I guess you would say problem, but the real difficulty here is the limitation with the phase grading diffuser is that it is quasi-random phasing, but regardless, you still have a spatially periodic, you have a unit cell, and it just depends on how big you can make your unit cell. Is it n equals 7? Is it n equals 20? You know, what is it? That's a design decision. And so because of that, you will always have grading lobes because there is still some level of periodicity in the system. Another limit, which isn't necessarily obvious and it's not necessarily a bad thing, is that all the energy that's scattered off is scattered at the frequency of the incident wave, clearly, right? It's a linear system, right? And so if you want a nice diffuse field, you don't want these lobes. As a matter of fact, what you really don't want are these nulls, right? What you would like a diffuse scattered field is one that not only gets extended in time, but gets a perfect plane wave goes off. It's incident in one direction and all energy is scattered off equally in all directions. That is a perfect diffuse field. So those are what we really don't want. Okay, and there's no way around those unless you make it infinitely and perfectly random and infinitely long, which we really can't do. So we were, you know, with the background of some of the things that we've done in non-reciprocity, we happened across some work in optics on these ideas of metasurfaces whose input admittance is varied in space and time. And you could take this group here in 2015, looked at the case where they had an incident wave field from one particular direction on this modulated field. They recovered the modulated surface, they recovered the signal, they time reversed it and showed that you didn't get the same reflection back, right? So kind of a ground, you know, 0th order verification of what you might expect theoretically. And more recently, Shanhui Fan's group at Stanford showed some really interesting stuff in actually going ahead and taking incoherent waves and combining their power structure by tailoring the modulation function of a surface. So you could take incoherent waves from different directions and focus them off in a single given direction based on how you chose the modulation. So really interesting stuff. So in an application to acoustics, we thought, well, you know, almost like, let's just try something fun and interesting. Can we use that kind of modulation of a metasurface to improve diffuser performance, at least based on the metrics that we have? And so the idea being in a 1D diffuser, where we had just like before, so why don't we look at the case where we have a static input impedance or admittance, right? Where we have our original distribution based on this QRD or anything else that we decided to work with. And then on top of that, we add in a modulation, which in this particular case, let's just assume it's a cosine-like function with a magnitude y sub m and a modulation frequency omega m and a modulation wave number, which is 2 pi over the wavelength k sub m. Okay, so when we do that, the difficulty becomes non-trivial just in terms of modeling. So what I'm going to talk about now is how you model it in order to predict the behavior that you would get. That would enable you to get an idea of how well this may perform or how interesting the behavior may be. And then it will give us an idea of what we want to be able to design and build in order to show some interesting response. So if you go back to that grading equation now, the biggest thing to point out here is clearly the incident wave. Okay, we still have our incident wave. We're incident on a diffuser of large period lambda, but now our input impedance Z is now a function of both space and time, okay? And so we still have the same incident wave, and we still have generally speaking, the same construction for the scattered wave as a summation of Bragg order, diffraction orders. Okay, and we still have the same projections along X and Y. But now the difference is that we have the wave number here that we need to match to along the surface is based on the modulation frequency, because we potentially have, what we effectively have, I should say, is we have a boundary condition of our half space, which is a time varying boundary condition. Okay, so it's linear still, but it's a time varying boundary condition. And since we have a time varying boundary condition, we have to be able to at least assume that we may have energy in harmonics of the frequencies, harmonic numbers of the modulation frequency, plus the background frequency of the incident wave. And so what that means is that our diffracted fields are not only our usual diffraction orders of the specular and order n, but also those associated with omega naught and plus the modulation frequency omega naught minus the modulation frequency. And those are going to be given by k sub p. And therefore, the theta, the direction, is also changed. Okay. So how do we deal with this? Well, we deal with this by saying that the scattered field amplitudes are actually a function of time as well. Because since my boundary is changing with time, the scattered field in any position has to be a function of time, not just based on the incident field alone. Okay, so if I look at that, then I can get that as a function of time as a Fourier expansion of the amplitudes for the specific diffraction order and modulation frequency order, harmonic, times e to the, should be j, omega naught plus p omega sub m. And what we want to know is the scattering magnitudes that make up the time-dependent solution for each n pth mode. So the nth diffraction order and the pth harmonic of the modulation. It's a lot of terms to keep track of here. So, and then when we do that, then we know that for that specific modal amplitude, that will get scattered off in a direction based on the harmonic number of that particular one. And where this is the case where there's no modulation, and now we have a modulation factor. Okay. All right. So how do we solve this? And this is actually, we spent a tremendous amount of time doing this in an FTA before. So what we want to do is we want to also define, in order to match our boundary condition, we want to define the modulated surface admittance itself as an expansion of the harmonics of the modulation frequency. Okay, so in other words, our input admittance here is defined as a normalized admittance. Okay, so it's a ratio of the background impedance, rho naught, C naught. Okay, and the admittance of the surface is Z. So you have the static Y naught plus your modulation, where your modulation now is some modulation function which you choose, which is this cosine function that we had before, right? But you can express that as a Fourier series as well, clearly. Okay, so when I do that, then I know that if I take basically my normalized admittance and I multiply it by the total pressure that exists on the boundary, which is the incident pressure and all the scattered wave, scattered pressures, then I get my particle velocity in the Z direction. Okay, and I know that my total pressure field is the incident wave plus the scattered wave, which is the summation of all these Fourier components for diffraction orders and modulation harmonics. I won't bore you with the details. You can just see where it fits in exactly. Okay, and then we also know that the input admittance is a function of the static admittance and the modulation function and the modulation depth, which in principle we could choose both of those. So there's sort of our new design variable, if you want, our new control on the diffracted field or the scattered field. And then once I calculate those things based on any given combination of harmonic and diffraction order, I can take this, normal velocity field and substitute it in to my conservation of momentum equation, and I can solve for the total scattered field. And it's a big mess, and I'll show you here in a little bit. So the scattering field amplitudes are now in matrix form, okay? We are going to assume a given modulation amplitude and frequency. Okay, so we're going to define our modulation, and that could nominally be anything since it's just a Fourier series. We're going to pick a simple one, nice cosine wave. And then we're going to use orthogonality and truncate the number of harmonics to where there's negligible energy in each harmonic. Okay, and then we're going to end up with this really messy equation. And I won't bore you with all the details, but essentially what it is you've got, you have for the pth harmonic, okay, modulation harmonic, you've got all of your diffraction orders for every single harmonic, okay? And you have this over here is basically your incident wave and your function of your modulation of your surface. And you want to solve for your scattered wave field for any given harmonic and sum of all the diffracted orders. And so basically you're going to invert this, which has entirely to do with the system. This is a function of the system and the modulation. And we're going to invert this big matrix to solve for all of our scattered wave amplitudes for every single diffraction order and modulation harmonic. So it's a big one. It's a size 2n plus 1 times quantity 2p plus 1 vector of components. Okay, so our simple example case, I'm almost done here, folks, is a nice 1D QRD system, just like we've been looking at. We're going to design an n equals 7, which just has to do with the number of wells in the system. 5 kilohertz design, so the design wavelength is 6, almost 7 centimeters, and the width of is 120 millimeters. And so here's the surface admittance profile that you would get from that particular thing. And then the idea is then we're going to have a modulation function, which I'm going to show here. So you take that modulation in every position of the well. I'm going to modulate that as a function of time. It's basically a discretized sine wave / cosine wave. And then if I look now on the right, what I'm going to see is basically the dashed red line is the static admittance, and then the solid blue line is the modulation of the total input impedance, or the imaginary part, the susceptance. Okay, so let's look at a case of two periods so that the scattered field is, we've got a symmetric scatterer, okay? And we're going to pick a modulation amplitude of 1.3. Now that is relative to the input in the impedance of air. So 415 rails, if you're familiar with that. And 500, basically a tenth of the modulation frequency is about a tenth of the frequency of operation. Okay, so what I'm going to explain here really quickly is the scattering amplitudes of the diffracted field. So what I've got here is the modulation harmonics. So the surface color is basically representative of the magnitude of the energy. So the energy in each of the harmonics and the diffracted orders. So what I have here are the harmonics. This is basically the frequency. So if the harmonics are 0, that means there's only energy in the incident at the incident frequency. And then the diffracted modes or the diffracted orders are here. So you can see that in the static case, this is our case where we have a certain amount of energy in our diffracted field that's all scattered off in different directions, but of course is only at one frequency. Okay, so now what I do is I apply that modulation, and I can modulate it to the left or the right. Okay, and I'm going to get a slightly different behavior because it's non-reciprocal. So bring it all the way back. Okay. When I do that, what you see is in a lot of ways, is quite dramatic. Now, because what you can see is now all of a sudden, not only do I get energy scattered in, so here's my 0, my incident wave frequency, right? I have considerable amount of additional energy scattered off in other directions via the diffraction orders, but also scattered off into harmonics of those directions and of the modulation frequency. And what you can see here is sort of a mirror reflective symmetry, if you want, for modulation to the right versus modulation to the left, or forward and backward, if you want to think of that, which makes sense. The thing is ultimately a linear system. It should look that way, but it is not, it would not obey time reversal symmetry. Okay, and so what this means, if I look at this in terms of the actual polar plots, in other words, the energy is a function of angle at a single frequency, is basically this. If you look at the non-modulated field, and actually let me just skip to this. So what you can see here is the dashed line is the polar plot of the scattered energy for the unmodulated case. And the solid lines are either for the forward or backward modulation. They should be the same. They're just flipped, okay? And so here you can see there's a considerable amount more energy off specifically at the low angles. And in general, considerably more diffraction of acoustic energy. The one thing I did want to say about this is that the energy, the main point of this is the energy is now scattered off in many directions and also at many frequencies. And I like to think of this a little bit in terms of something like turbulence. Okay, imagine you've got a turbulent wave energy, you get your initial sort of perturbations, which are pretty periodic in both time and space. And as the turbulence sort of increases, you scatter energy off into smaller and smaller length scales and smaller time scales. And it's a similar idea, at least other than it's linear. And we have control over it. Okay, so what we did do is we wanted to verify that this was right. So we actually ran a time domain FEA model where we had an incident wave, and then we looked at just a sample in 2D. And the no modulation case you can see is here. It's not perfect. We're working a little bit with the FEA because the boundary conditions at the base is not the same. But in general, what you can see is a lot more energy scattered off in all directions, as you would expect. So let me just show you what that means, because that's actually more meaningful. So on the left-hand side, you're going to see we have an incident wave for non-modulated QRD, then a modulated case in the positive X direction. And what you're going to see on the next slide is basically the animation of the scattered wave field and only the scattered field. I've just pulled out the incident field. So as you can see on the unmodulated cases, even though, yes, energy goes off in many directions, you still kind of have a beaming sort of effect due to the periodicity. And you can see with the modulated case, there is maybe some preference for certain directions, but it is it's much more chaotic and it's much more diffuse. Okay. All right. So, and then the last thing I'm going to say with respect to this, this is known as the diffusion coefficient as a function of frequency. The dashed line is the unmodulated case. The solid line is the case where it's modulated. These are increases of 20, 30%, which is actually quite drastic for this kind of thing. Okay, so the last thing I want to say is this has all been models, right? And so, what are we really going to do with this? What can we do and how can we actually implement it? And that's the next steps. And we've done more than I'm, showing here. But the tack at this point is to look at some activated compliant surfaces at the base rather than a rigid base. So I have a termination impedance, which is a type of compliance. And I can use, the objective here is to use a shunted negative capacitance impedance, finite number of those in order to adjust. Again, that termination impedance just really has to be a change on the order of the impedance of air. So it doesn't have to be a huge change, but it does. And this still is, we're still working on it to see if we can get what we want to get. So it could be
that's
tough.
gonna be my question is like, how are you going to get 30% change? And so you're still working on it.
We're working. It seems more tractable than I first thought, but I'm not going to promise anything. Okay, so yeah, it's worth a try, right? So construct our capacitor circuits. We're going to measure them in our impedance tube, and then just go straight ahead and look at it in the anechoic chamber. Okay, so I'm going to summarize because I know we're a little long. Started a little bit later. And a little bit of an outlook here. So reciprocity, we can break the principle of reciprocity by modulation of material properties, also surface admittance. This gives us a lot of new concepts for wave control, although they're all arguably somewhat out of reach because there's some real scientific challenges. This one that we're talking about, I would argue, is an engineering challenge. It's a technical challenge. I think it's doable on a surface. In the bulk of a material, I think it's a lot harder problem, but it's a really interesting one that hopefully we can get to. It's Interesting to note that diffuser performance is greatly improved in terms of just that diffusion coefficient. We are scattering both in time and space, so that gives us a lot of advantage. It also gives us an ability to control it with a knob, right? This is not hard, it's hardware, but it's a programmable surface, which is really quite interesting. So there are some real serious questions about perception. Do I want to put this in a recording studio? I'm not convinced. Would it work great in a restaurant or something like that, where I could maybe add in a little absorption and kind of help with some backslap or something like that? I don't know, maybe. I can think of other things too that may be, not audio related that may be really quite interesting with this. But I think the main takeaway is that the research partnerships here in sort of material science and a lot of, electroacoustics and system designs is really kind of important to get this to the next level. So, thank you all for your time. For those of you that are online and managed to stay through it, I appreciate it. Feel free to ask any questions you may have. All right.
All right, questions for our speaker?
Yes.
Oh, go to Nate.
Hey, I was a little confused about the last part with the shunt circuitry and how that connects to the variation in depth of your cavities. How are you?
So, yeah, so actually, I'm not going to vary the depth.
Oh, okay.
Sorry, I turned that off so we can get feedback. Yeah, I'm not going to vary the depth. And actually, there's one primary reason. So the depth variation will create sound. So if we're modulating at 500 hertz, we're going to get a low tone, and that's not great. So maybe you could modulate way, sub, infrasonic, but that probably is going to cause all kinds of problems too, power, everything else. The idea is to make that termination compliant with an adjustable level of compliance. So it needs to be a bending type of emotion, right? So you can imagine basically the compliance of a well is just the air cavity compressing. If that termination is now you have two springs in series. That spring in series with a piezoelectric or some other maybe construction of the piezoelectric may not be just a simple plate or PVDF or something like that. But that in and of itself, as you adjust it, given its electrical boundary conditions, I just need on the order of 30-something% of the air impedance change. So that's the answer. Yeah, movement. The first thing we thought of was just in principle, you could still show this by literally just mechanically moving these, but I think what you'd end up with is you'd hear the modulation. I think that's all you'd hear. So.
Speakers.
Yeah. And, and frankly, I mean, yeah. And the one thing that's very intriguing about this is you actually have, it is a powered system, but it's not an active system in the sense of, feeding acoustic energy out, which is a slight distinction here. So.
Yeah, so that I think changing the impedance at the end, that won't generate sound.
It may, but it won't as much as true motion.
Well, especially the 30%, right?
Yeah.
Like you said, that's going to be
Yes.
That's going to be really good. Problematic problem. And then you mentioned it on your slide about perception, right? And
yes.
That's one of the biggest things if I'm in a musical environment, I'm expecting even with diffuse sound or even in speech to not have this modulation of a 500 hertz tone.
Right.
Do you have any idea how that we might perceive that? It might make you nauseous.
So
or not, I don't know. You know what I mean? Like,
no, I'm really intrigued. So I mean, and not just intrigued. I mean, one of the reasons that I didn't throw it out of hand is I can think of other things that aren't audio related that it will be useful for. But
I'm not saying it's not useful. And but the application is cool. But yeah,
it's a real
modulating town.
So
did you look up
what I've done? No. So it's funny. We just really actually started getting into the audio, truly into the audio part of it, because we weren't sure at first what we were going to really get out of this. Our first steps that we're looking at are just different metrics associated with audio quality. There's a lot of them both in correlation coefficients and all sorts of things. in
Oh,
terms
I'm
of-
just talking about perception for now.
Well,
Yeah, I
right.
wonder, you know, like, will it
Well-
sound good or not? And you may not know. I don't
So
know.
we've oralized some of these,
Uh-huh.
and they're, you know, you can hear it.
Yeah, because you could simulate.
It's not a pure tone,
Yeah.
so you can hear it. And what I meant when I was talking, there's a lot of different perception metrics out there that talk about like roughness of tone and things like that. And it actually reminds me a lot of that. And you play two tones close together and they start getting too close or too far, where, you know, consonants and dissonance and things like that. And I think it may not be pleasant for certain cases. So one question that we had was, can we actually pick the modulation such that it is more pleasant? And which is clearly an open question. It's a one that's harder to answer because
Absolutely.
there's probably are not many perception metrics that exist that are really sufficient for it.
And then I do want to make one small comment about your non-reciprocity examples that you gave. I believe you missed two. So
Okay,
the ones that we did.
yeah,
And also with Bob.
I know, I grabbed some.
Humbly submitted.
I will be more than happy to add them. I was digging around for some, I knew bug, because when we had the Muri project, I grabbed yours on purpose. The guy that got me here, I had to make sure to get it. Anything else?
So your diffuser, is it generating sound only at that 500 hertz modulating frequency, or are you creating sound at other frequencies as well?
Well, so its other frequencies are scattered off.
Right, are those just, generated by your active, motion of the?
Well, and again, this assumes it's just the impedance that's changing. I agree that it may make a sound as you vary that electrical field. I think there's, how it radiates and all that's maybe a little different question, but we're going to find out.
Right, that's interesting to figure out.
But what it is that, if you look at this, these are all of the frequencies, and they are in principle an infinite sum
Right.
in order to match the time and space varying boundary conditions. So each diffracted order has its own, each modulation frequency has its own diffracted order, right? And so that's why you get this kind of just smearing of energy into all these spaces. And actually, one thing I did want to point out, because one of the very first things I asked that we checked is in the propagating modes, there's some of these are outside the propagating band. Some of these are evanescent, also here.
The radiation circle.
So yeah, so your radiation circle, and it's not symmetric. So it's but even some of these are the same thing. But the total energy in all cases is the same within at least our numerical order error, which is interesting.
Yeah, and the cool thing about all these systems is because you have spatial modulation, you generate these harmonics and a whole
Yes.
bunch of them. If you just had it still, you'd have two tones.
That's right.
And that would be
And that's it.
Yeah.
Yes.
Yeah.
And there is something to be said here as well, which is if you look at this, and I of course didn't show this as well, is that if you just looked at it where you had a flat surface and then you just modulate it, then you don't get nearly the smearing of energy. And actually, the more finely you discretize your wells, you also actually get a little bit, the discretization kind of helps you because it's almost like a fringe, a Gibbs type of effect. Yeah. And I mean, this is sort of very qualitative, just seeing but it's kind of like a Gibbs effect. It's almost like you want that Gibbs phenomena where you get these little extra harmonics that exist. In order to match, you got to get more and more orders in order to capture these sharp changes. So anyway.
What were you simulating then in the finite element?
So the finite element, yeah, and that's actually why we had a little trouble getting, as good of agreement here as we'd like. But what we simulate in this is this boundary, you can just prescribe the input of it. So it's the simplest one to make sure it matched as close to the analytical one as we could. And actually, we're kind of debating whether we want to simulate the full system or just go straight at it, which is probably more what we're going to do experimentally. So this one's just a prescribed impedance, but static, and that's the same one, but with the modulation.
So just the equation.
Just the equation. And that just, again, it made it a little less prone to other errors for a true A to B. The reason it's hard to get the analytical to match is that in reality, this is a surface kind of in free space, that just gets absorbed as it goes by. And so getting that to match the analytical solution where you basically have scattered field only on this boundary, the effects of the edges and stuff are a little bit different. So that's why these all come down to like a 0 off on these directions.
Yeah, that match is pretty good. So I'm
It's
just
pretty-
curious, what kind of, solver did you use in order to get the, time domain variation?
So the COMSOL, it's COMSOL, which one was it? We wrestled with this a little while because there's the newer packages have better time domain simulation. And I feel like it was one of those because we did struggle with it a little.
Yeah.
I'll look it up for you.
No problem.
It's good to know
I
because,
struggled a lot.
yes,
Simulations, time domain simulations, so it's good to know that they have better solvers now.
it's gotten a lot better. And with like the PMLs still as well, the match layers still seem to be pretty good. So, yeah.
All right, thank you very
Okay.
much, Mike.
Yeah.
It's already 10 minutes. past
All right.
5.
Thanks for trooping, everybody.